In a mission unlike any before, NASA launched the Parker Solar Probe, a spacecraft designed to do the impossible, touch the sun. But just like how modern technology can push the edge of what's possible, it also faces moments of danger. Recently, Delta Airlines Flight 446 took off from Los Angeles, but had to return and land due to an engine fire. A Delta spokesperson told the BBC that the flight made an immediate return after detecting a malfunction in the left engine. Whether it's a spacecraft soaring toward the heart of our star or a commercial flight facing critical decisions, every journey into the skies comes with both risk and resilience. Now, back to the most daring space mission ever attempted. Shielded by a carbon, composite heat-resistant shell, the Parker Solar Probe endures temperatures of nearly 500 degrees Fahrenheit as it travels closer to the Sun than any human-made object in history. Each orbit brings it nearer, using Venus's gravity to slingshot closer and closer, aiming to reach just 4 million miles from the Sun's surface. That's 7 times closer than any spacecraft before it. Its mission: to unlock the secrets of solar winds, magnetic fields, and violent solar storms, phenomena that shape space weather and can knock out satellites, power grids, and disrupt life on Earth. This isn't just science, it's a journey to the heart of a star where no spacecraft has dared to go until now. NASA's Parker Solar Probe holds the record as the closest human-made object to the Sun, traveling within just 3 million miles of its surface. Launched on August 12, 2018, from Cape Canaveral aboard a Delta Roman 4 heavy rocket, the mission was named in honor of astrophysicist Dr. Eugene Parker, who first theorized the existence of solar wind in 1958. The probe is designed to study the Sun's outer atmosphere, known as the corona, where temperatures soar into the millions of degrees. Despite these extreme conditions, Parker is able to operate due to its innovative thermal protection system, a heat shield made of carbon, composite materials that keeps its instruments at roughly room temperature. The spacecraft is traveling at incredible speeds, reaching up to 430 miles per hour, making it the fastest object ever built by humans. To achieve its close orbit, the probe uses a series of 7 gravity-assist flybys of Venus, slowly tightening its path around the Sun with each pass. The final closest approach is expected by 2025, when it will reach its minimum distance of about 4 million miles. For perspective, Mercury, the closest planet to the Sun, orbits at about 36 million miles away. The mission's main scientific goals include understanding why the Sun's corona is so much hotter than its surface, how solar wind is accelerated, and what causes solar energetic particles that can pose risks to astronauts and technology. The Parker Solar Probe is equipped with 4 major instruments: fields to measure electric and magnetic fields, whisper to image the solar corona, sweep to count solar particles, and ICES to detect energetic particles. This data is helping scientists predict solar storms more accurately and protect satellites, astronauts, and Earth-based systems from dangerous space weather. The Parker Solar Probe's ability to survive the extreme environment near the Sun is made possible by its revolutionary heat-defying technology. At the heart of this protection is the Thermal Protection System (TPS), an advanced heat shield composed of carbon composite material measuring 5 inches 43 centimeters thick. This shield can endure temperatures exceeding 500 degrees Fahrenheit, about 377 degrees Celsius on the side facing the Sun, while keeping the scientific instruments behind it at a stable room temperature of around 85 degrees F, 30 degrees C. Without this technology, the probe would not survive even a fraction of its journey. The TPS has a white ceramic coating on the front to reflect as much solar energy as possible. It was rigorously tested on Earth under simulated space conditions to ensure it could endure intense solar radiation and high-velocity dust impacts. The spacecraft's systems are tucked behind this shield, including solar panels that retract when the probe gets closer to the sun to prevent damage, with only small parts exposed to collect energy efficiently. In addition to thermal protection, the spacecraft uses an autonomous guidance system to keep itself oriented correctly. If the probe's instruments start to drift from the protective shadow of the heat shield, the onboard system corrects its position instantly without needing instructions from Earth. This is critical because communication signals take minutes to travel from Earth to the spacecraft, and real-time manual control would be impossible at such close proximity to the sun. The materials, engineering, and autonomous systems combined make the Parker Solar Probe a marvel of modern space technology. It is the first mission ever to fly into the sun's corona and return valuable data, all thanks to the protective barrier that allows it to touch the sun and survive. The Parker Solar Probe was launched on August 12, 2018, from Cape Canaveral, Florida, aboard a Delta Roman 4 heavy rocket. Its mission is set to last approximately 7 years, ending around 2025. To achieve its goal of getting closer to the sun than any spacecraft before, the probe uses a series of 7 carefully planned gravity assist maneuvers around Venus. These flybys are not just for navigation. They allow the spacecraft to gradually tighten its orbit around the sun, reducing its perihelion closest point to the sun with each pass. This method saves enormous amounts of fuel and enables the probe to reach speeds of up to 430,000 miles per hour, making it the fastest human-made object in history. The gravity assists involve Parker passing as close as 1,500 miles from Venus's surface, using the planet's gravity to pull the spacecraft into a tighter orbit. With each orbit around the sun, Parker dives deeper into the corona, eventually reaching a distance of about 4 million miles from the sun's surface. This is more than 7 times closer than any previous spacecraft, including Helios 2, which held the previous record of about 27 million miles. The spacecraft's orbit is highly elliptical, allowing it to spend short periods close to the sun while avoiding prolonged exposure to extreme heat and radiation. Between solar encounters, the probe transmits vast amounts of data back to Earth, captured during its close approaches. The mission is a coordinated effort led by NASA's Goddard Space Flight Center and the Johns Hopkins University Applied Physics Laboratory, which designed, built, and manages the spacecraft. Each pass yields more detailed information, bringing scientists closer to understanding the dynamics of the sun's atmosphere, solar wind, and magnetic fields, phenomena that have puzzled astronomers for decades. One of the primary objectives of the Parker Solar Probe mission is to gather data on the sun's corona, solar winds, and magnetic fields, elements that play a major role in shaping the space environment around Earth and throughout the solar system. The sun's corona, its outermost atmosphere, is a region of intense scientific mystery. While the sun's surface, or photosphere, has a temperature of about 0 degrees Fahrenheit, the corona above it reaches temperatures of over 1 million degrees Fahrenheit. This counterintuitive heating has puzzled scientists for decades. The Parker Solar Probe is designed to fly directly into this region, capturing real-time measurements to help solve this mystery. One key focus is understanding how solar wind, streams of charged particles constantly emitted by the sun, are generated and accelerated. These high-speed particles interact with Earth's magnetic field and can disrupt satellites, GPS signals, communication systems, and even power grids. Parker is equipped with 4 instrument suites: Fields, which measures electric and magnetic fields; Whisper, a camera that images the solar corona and solar wind structures; Sweep, which counts and characterizes solar particles; and ISIS, which studies high-energy solar particles. The data returned from Parker has already revolutionized solar physics. For example, it detected sudden magnetic field reversals called switchbacks, revealing complex magnetic behavior in the Sun's atmosphere. These findings suggest that the solar wind may be more structured and turbulent than previously believed. Additionally, Parker's close passes allow researchers to pinpoint where in the corona the wind originates and how energy is transferred outward. The ultimate goal of the mission is to build a predictive understanding of space weather. By identifying how solar storms begin and travel through space, scientists can better forecast their arrival at Earth, crucial for protecting modern technology and human life beyond our planet. The Parker Solar Probe mission is not only a triumph of exploration, but also a vital step in protecting life and technology on Earth. One of its key contributions is improving our understanding of space weather, phenomena driven by the Sun, including solar flares and coronal mass ejections (CMES), which can have serious consequences for modern civilization. When these high-energy solar events occur, they can send massive amounts of charged particles hurtling toward Earth at high speeds. If they collide with our planet's magnetic field, they can disrupt satellite operations, damage spacecraft, interfere with GPS and radio communications, and even cause power grid failures, as seen during the 1989 Quebec blackout. By flying directly into the solar corona, Parker is gathering data on the source regions of solar wind and solar storms. This allows scientists to study the conditions that lead to major space weather events and better predict when they might happen. The probe's instruments provide detailed measurements of particle flows, magnetic fields, and solar wind structures, information that is critical for forecasting space weather and issuing early warnings. In the future, this knowledge could give astronauts in space, especially those traveling to the Moon or Mars, valuable time to seek shelter from dangerous radiation bursts. Parker's observations are already helping space agencies model solar activity with greater precision. For instance, the detection of solar switchbacks and turbulence in the magnetic field near the Sun is helping researchers understand how energy is transported through space. These insights support the development of improved models for how solar storms travel and evolve. Ultimately, the Parker Solar Probe is more than a scientific mission. It is a guardian in the sky, protecting technology, communications, and life itself from the invisible threats that originate 93 million miles away at the heart of our solar system.